code has finally been graded and posted. I just got them back from my TAs today. So if you go on Blackboard, you should see your scores. I brought them with me, so I will pass those back at some point when you guys are working on practice problems during the day today. The next homework assignment has actually been posted on the course website. So it's already up here. It deals with finite state machines, flip-flops, that kind of stuff primarily. It's due 1 week from today, so next Thursday is when that's due. Again, this is an individual assignment. And I want to reiterate, because I saw this a lot on the last homework assignment, that if you put collaborated with so-and-so on the top of your homework assignment, that does not mean you get to turn in the exact same answer to the problems as that person, right? I saw that a lot. I'm not going to do anything about it this time. If I see it happening, keep happening on the next homework assignments, then I am going to start doing something about it. So please, please, please be aware of that. You are welcome to talk to people about these problems, right? That's what it means to collaborate with somebody, is strictly talking. If you're looking at their answers, if they're looking at your answers, then you are over the line. And I'm going to start being more strict about that. So if you're ever in doubt, please, please, please ask myself or the TAs. I think that's about it in terms of announcements. Let me just see if there's anything else coming up on the calendar that we need to be aware of. I don't think so, actually. Oh, yes. Chapter 3 of the Xi book is also due 1 week from today. So we're going to cover the last couple topics of the Xi book. So that Xi book is due 1 week from today. And we actually have exam 2, it looks like, coming up in, let's see, that'd be 1 week, 2 weeks, 3 weeks. Okay, so we still have 3 weeks. That's kind of a long time. So not quite time to worry about that just yet, but pretty soon we are going to need to start talking about the next exam. All right, cool. Any questions before we dive into today's stuff? Yeah.
Sorry, chapter 3 is due this coming Thursday.
1 week from today, yes, October 15th. That's correct. Yep. And as usual with that, you usually don't need to complete every single last thing. I think the threshold I've been using is about 95%. So if you got 95% of the stuff, then you usually get credit for that. Okay, cool. So today we're going to be talking about code. Code. We're going to be writing a lot of code today, as a matter of fact. But before we do that, let's talk about something a little bit different first. Who can explain to me what a lookup table is, how a lookup table works, what we use them for? Note takers? Yeah. Exactly, right. So when you, like what you did for Lab 2 and what you're going to be doing on the rest of the labs, when you write that code and you put it onto the FPGA, the circuit board, it's not actually constructing all of those gates. It's not actually putting all those gates together to form your circuit. It's just computing what the output of that circuit should be and storing it in a table so that it can just look it up. Right? That's how the FPGA works. On this circuit board, we have, we call them 4 input lookup tables, so they can take 4 input values. And they can do anything they want to those 4 input values, right? ANDs, ORs, doesn't matter, NANDs, NORs, doesn't matter what the operations are. They can take 4 inputs and give you 1 output, right? In more modern FPGAs, if you go out and spend some money and buy some fancier ones, you might find 6 input lookup tables or even 8 input lookup tables in some of the more higher end FPGAs. What is a configurable logic block? This is definitely in the video. What do those configurable logic blocks contain? Can we tell me some of the pieces that are inside of there? Some of the stuff that might be in a configurable logic block? Yeah. Lookup tables. Yeah, we'll find at least a few lookup tables in there. What else am I going to expect to find? Stuff that we've been talking about recently. Yeah, go ahead. So the function generators are the lookup tables, so that's correct. Yeah, lookup tables are function generators. What other pieces? What have we been talking about a lot recently? Flip-flops. There's going to be some flip-flops in there. So if I want to do storage, I can do that in my configurable logic blocks, which is good because most of our circuits are operating with flip-flops recently, right? There's also some configuration stuff, so multiplexers and wiring and stuff like that we're not going to spend a whole lot of time talking about. The big things are lookup tables and flip-flops, right? Those are the two major pieces, lookup tables and flip-flops. With those two components, we can really create any circuit that we need to string together whatever circuits we want, at least for the purposes of this course. All right, so let's just do a couple more exercises with lookup tables. These questions shouldn't take you too terribly long. There are 3 questions here that I'll ask you. How many lookup tables does it take? The last one actually asked you to sketch some lookup tables. Take 2 or 3 minutes, or maybe 5 tops. Talk to your neighbors, and then see if you can figure out the answers to these guys. Oh, we're using 4 input lookup tables for these as well, right? 4 input lookup tables. So what are we thinking here? How many lookup tables do we need for an 8-input mux? It's not a lot, right? Yeah. 2 of them. Okay. What makes you say 2?
Well, each one takes 4 inputs and the later flip-flops.
Yep. Okay. Any other suggestions? So an 8-input mux, just to give us a little refresher, right? 1, 2, 3, 4, 5, 6, 7, 8. Output. What else? I need select bits. So if it were just these, might be able to get away with just 2 potentially, right? But I have these select bits as well, so that's gonna make 2 lookup tables tricky. Can I do it in 3? What do you guys think? Does 3 work? So we have to consider that if I'm combining lookup tables together, right? The outputs of some of my lookup tables are going to consume inputs of my other lookup tables. So if I take these 4, for example, and group them together in one lookup table, right? So here's those 4. And then I've got another one for these, right? Well, I then have to combine the outputs of both of these as well as these 3 inputs. Can I do that with just one more? I don't see how I can do it. I've got these two as well as these three. That's 5 things that I need. So I don't think one more is going to cut it. I've got a lookup table here that'll take those two as well as 2 of my select bits, right? But then I need another one combined with the final select bit before I can get my result. So I think I need 4. I think I actually need 4. Anybody think of a clever workaround that would get this in 3 instead? So what then is the equation? So, for this next one here, there's actually a function, there's actually a formula that we could use to help us with this. What really is the formula, right? How do I do this? There's some factor of 4 involved. I can take the number of inputs and divide by 4, and that'll get me in the right direction, but then I actually need to combine all of those together as well. So, the number of inputs here is actually 11. Divide by 4 gets me, I need at least 3 to cover that, cover those 11. But then those 3 also have to be combined, so I need an extra one in addition to that. And actually, that should be the same for this one as well, right? 12 inputs and 1 output. So those 12 inputs I can feed into 4 different lookup tables, but then I'm going to need another I'm going to need another one, or I'm sorry, 3 lookup tables, not 4. Sorry, I misspoke. But then I'm going to need another one to combine all of those together. So it's really a function of my inputs and outputs. You see that? Divide the outputs by 4, and then actually take a look at how many of those you have, and then determine how many lookup tables you need then to combine all those together. And that's your result. It also depends on the number of outputs as well. These are kind of simplified cases. Yeah.
Oh, I should ask. So do you always need one at the end to combine all of your inputs like that?
Yeah, you're always going to need at least one at the end to combine. I mean, if I have one output, right, then I need just this guy right here, this single output, right? Just getting me this, just getting me this far in this case isn't enough because I still have one input left over. Just using 3 lookup tables to track these 12 inputs isn't enough because I actually want to combine all that stuff together. Right? It's not enough. I need to combine it all. I need to condense it all together. So something like this here, right? We see I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we know, kind of based off of math and the other ones that we've looked at, I can do this in how many lookup tables? Tempting to say 3, but resist the urge, right? Actually 4. I'm going to need that extra one to combine them all together. Right? So it would take 4. See if you can sketch it out. Right? If you're ever in doubt, just draw it, and then it should be immediately clear how many you need. Any questions? Yes? Sure. Uh-huh. Yeah, so that's a great question. I mean, let's take a look at this last one as an example, this last equation here as an example, and see if we can compute exactly what would happen. Remember, these lookup tables, they don't care what operations are being performed. They just care about what goes in and what comes out. So, if I start trying to piece this together, I might just choose, A, B, C, and D to feed into my first one, right? And that comes out. And then I need the rest of these as well. So I have to be a little bit careful with the parentheses here, right? F, G, H, I, and then J, K, and L. So we have to be a little bit careful. I might actually choose for my second lookup table, I might choose E, K, and L. That's 3 inputs, right? So that helps me get this evenly into this lookup table here. And I've covered this term now, as well as this entire term. So the only thing I have left is this one in the middle, right? So what is this actually computing? This is A or B or C or D. What's this one computing? This is A or B or C or D. ANDed with K or L. I can do that. I mean, it's still a valid piece of my equation because of the associative property, right? Commutative property. Which one is that? That's commutative, right? So that's okay. And so then I just need to piece this term together in the middle. It has 5 terms, so I can stick 4 of them into one lookup table. F, G, H, and I can all go into one lookup table. I need J as part of the last one. And then I can take this one and feed it in as well to this last one. J, and then this all go into my final lookup table. And then my result is right here. Yes?
Wait, sorry, so where does E feed into the second one?
Oh, I'm sorry, I just forgot to write it. Thank you. I just forgot to include that in. Thank you very much. Should go right there. Yes?
So what's like
The number of inputs and outputs. Yeah, so I have a, 1, 2, 3, 4, 5, 6, 7, I think I have 12 here, is that right? 3, 4, 5. Well, this is also, these are actually equivalent in terms of number of tables. They should be 12 inputs, 1 output. It doesn't matter what the actual equation is. That is irrelevant to how many lookup tables I need. It's based solely on the number of inputs and outputs. So if I have 12 inputs, consider I'm going to need at least 3 lookup tables to cover all 12 inputs because they have 4 apiece. And then I'm going to need at least 1 more to cover combining those 3 together, right? So we think about, how would we write that out as an equation? I'm going to need, I'm sorry?
The ceiling of your number of inputs divided by 3.
Ceiling of inputs divided by 3, oh, that's not. Ceiling of inputs over 3?
Yeah. Because what you're doing is you're doing your number of inputs plus your number of lookup tables divided by 3 equals your number of lookup tables. Because each lookup table is going to add 1 output, which then has to be considered as an input.
Each lookup table is going to add 1 output.
Maybe it's your number of lookup tables.
That's
1.
So in this case we get 12 over 3, which is 4. That's correct. But what if we do, so 13 then puts us over the edge, right? That would be 4 point something, which would require an extra lookup table. That would give us 5. I think you're absolutely right. 3 is acceptable here because one of our outputs is going to be fed into the input of another lookup table, and we have to account for that somehow. This is only, I believe, valid if we have a single output at the end. If we start adding additional outputs, then this is no longer going to work for us. So we could,
Yeah, I'm sorry. I asked a question about what if there's more than one output.
Yeah, so if there's more than one output, we have to take that into account as well, because we're going to need at least 1 lookup table for each output in our equation as well. So we can account for, you can reuse inputs, that's absolutely correct. Yep, you can reuse inputs. I actually have the official equation written down. Do I have it on this sheet of paper or is it on a different one? I have it on a different one. But this is the piece of it, I believe. Inputs over 3, take the ceiling of that, and then the other piece is plus the number, need at least 1 per output as well. So how does that factor into the equation? It would be might just be plus outputs. I'm not sure. That seems wrong to me. That seems wrong to me. Let me look up the official equation while you guys are working on the next problem. Are there any other questions on this before we move on to the next question? All right. This one's going to take you a little while. I want you to write VHDL code for this particular circuit. Before we do that, let's take a look at this circuit and see if I can give you guys a push in the right direction before it's turning loose. For starters, I don't care about the entity piece. You can write it out if you want. It's great practice, but let's just focus on behavioral for the purposes of this question right now. Right? So I want you to use a process, and I want you to use case when. Right? I don't have any flip-flops here. So that's going to make life a little bit easier for you. You're going to see flip-flops in a little bit. Where might I use case when? What could I potentially use case when to represent as part of this circuit? Yeah. The the decoder. Case when is going to be what we're going to use for this decoder. So we can see down here, I've got 3 bits coming in. It's a 3 to 8 decoder. So my case when statement, I expect to have how many different pieces? How many different branches in my case when? Yeah, 8, right? 1 for each of these guys. 1 for each of these. Okay, so break it down. It looks complicated. It's really not that much code. I think it's 10, 15 lines, perhaps, of code. See if you can work with your neighbors and figure it out. And I will start passing back homework assignments while you guys are working on this stuff, too. Let me know if you have any questions. It's going to be easier. One is actually connected. Oh, yeah. Wire. Yeah. Yeah, right. I like your name because you got the J. You got the J action happening.
I've been doing it for
And you are, boy?
Connor.
Connor, I'm sorry. There is a boy in this class. That's right.
It wasn't actually.
Oh, okay. Oh, this is gonna take a second. Something. Connor, got it?
Yes. Thank you. Yep.
Strong magnets. That's the best. I don't think it was me actually. Might have been. Yeah, the answer is hard.
So if you were, you would be happy if you all then you'd be happy with it.
X is always equal to A, and Y is always equal to
Oh,
C or D.
Well, that's what you're doing for the first one. Oh, come on. They made it. Why does it look at the C? It looks at the Yeah. Yeah. Yeah.
Okay, let's start to talk about this. I realize we might not be done. Also, I know I'm not done passing back homework yet. I'm going to keep doing that as we go throughout the day. So be patient with me on that one. But let's start to talk about this a little bit. Let's start with the decoder down here, right? I look at this decoder. I see I've got this input of P. So I know for a fact, right, how many of these outputs are going to be active at any given point in time? One. Just one. Exactly one, as a matter of fact, right? Exactly one. So what does that mean about these AND gates on the right-hand side there? Yeah. Only one will be active at any given point in time. All the others will be off. Right? So that really simplifies the work that we have to do in this particular circuit. So the way that we need to break this down is by, if 0 is high, then the output is going to be 1. If 4 is high, the output is going to be 1. And we have some cases that circumvent those AND gates that we'll need to figure out as well. Right? So let's take it one step at a time. Here I've set up the beginning of my process. What's this called again? Parentheses? Yeah. Sensitivity list. What am I going to put in there? Yeah. E, A, B, C, and D. Yeah, why did I do that? What does that mean? Well, what does it mean when you pass through the process? What does that actually mean? Yeah. Yes, anytime that one of these changes, the output's going to change. So this process isn't going to execute until one of these values changes. Right? That's how, excuse me, a combinational process works. We'll see a synchronous process a little bit later on. Okay, so now we can start to piece together our issue, our circuit. I'm going to do the decoder stuff. So I'll say case P is, and then I start listing out all the possible combinations of things that P can be. So P can be 0, 0, 0, right? When 0, 0. We don't need to include 0, 0, 1 because 1 isn't hooked up to anything. So P is 0, 0, 1, we just don't care, right? It doesn't matter. So this should actually be 0, 1, 0. Now I need 7 of
And when
these.
it's 1 though, don't we have to still give x and y their default values?
We will talk about what's going to happen with those actually in a little bit. You are correct. X and y do have values when p is 1. But we can cover that condition without specifying that in our case. So I will need 7 of these conditions total, right? When 1, 0, 0. This is a little tedious, but it'll be over soon. When I skipped number 1, yes. Because it's not hooked up to anything. That's what we were just talking about. It's not hooked up to anything. 1, 2, 3, 4, 5, 6. I got one more, right? Okay. So now I need to dictate what's going to happen for each of these particular cases. If it's not hooked up to these AND gates that are connected to the decoder, I'm not going to worry about that right now. I'm not going to touch it right now. I'm just going to worry about the stuff that's being fed into the AND gates. So one input is from the decoder, right? What is the stuff that's coming in on the other side? That's what I want. That's what I want this stuff to be. That's what I want this stuff to do for me. So, you know, I'm going to have some signal. I'll call it, I don't know, I guess I'll call it X and Y, right? As the case may be. And I'll just set this value. Well, X is a bad name because we need to take the default values into account. So this won't actually be X. I guess it's okay. You can do it a couple of different ways. In my answer key here, I actually have, you know, a separate signal here. This is sort of an intermediate signal that I would have to define up top somewhere, right? Signal X as a standard logic, right? It's just a placeholder, right? But then I'm just going to specify what I want X to be in each particular case. So for 0, 0, 0, I take a look, and it's A and B in that particular case. A and B. Right. For the next one, XA gets set to A or C, right? And you would just need to go down the list and do this for each individual case. This is not hard, I hope. Are there any questions? Yes?
For the first one, isn't it like A and B or A?
So the OR A is actually not dependent on the decoder at all. This case statement is only affecting the decoder. It's not handling anything that is not touched by the decoder. The decoder is controlling these AND gates, and that OR A is kind of sneaking around
But
the AND gates.
like, then why are we not part of that?
We are. We're just not dealing with it yet. We haven't
Is
gotten
that
there.
what you have in the intermediate X?
That's why I have this intermediate value, yes. That's exactly why I have it, yeah.
Why are you going to have an intermediary instead of just inside your case program?
So inside of the case, what would that mean? I would have to say OR A, right? For every single case that I have this, right? Every single time. I think it's faster to, down here, just say X is equivalent to XA or A, and now I only have to write it once. So it's just trying to make my code as efficient as possible. So that's how we code up the default values, right? It's stylistic. It's not functional, but it's definitely going to save you some typing. Yeah. I think that would work. I think that would actually, in fact, work. Again, it's just stylistic. I prefer to use the intermediate for that purpose. I don't think you'd have to. Yeah. So yeah, you could write OR A after each one of these if you absolutely wanted to, but you don't need to. You can just define that down at the very bottom. And so you just have to fill out the rest of these cases. I need another line down here for Y, right? Y is equal to YA or what is it? Or C or D. Ah, thank you. I was waiting for somebody to say that. I do need an others, right? Others is required. It seems perhaps maybe a little silly to require it, but it is in fact required. I left myself a little, just enough space here to stick it in. When others, what do I do? This may be something that you haven't quite seen before. What do I do when I have something that's not one of these values? You could, or you could just not change them at all, right? You just leave them how they were.
So the default state
I'm sorry?
So if you leave them how they were, you could in theory, like how does VHDL handle instantiation of variables? What's the default state when you instantiate signal x?
Unknown.
It's unknown, okay. So when you do unknown or a, what happens?
Well, let's think about it. If I do unknown or a, if a is false, the answer is what? Unknown. If a is true, the answer is true. Yeah. That's it.
So you're going to get unknown and x.
Potentially.
When you should have gotten a false.
Should I have gotten a false?
If a is false, you should get false for x. If you go into the case where it's 1.
Is that true, though?
Yes. But like if a is false and your decoder gives you 1, you should get false. You should get unknown.
If my decoder is 1, then none of these will be active, and a is false. Should I get false? Yeah.
So you do need to zero out x.
Okay, you're correct. I stand corrected. Thank you. Thank you for being persistent. You're absolutely correct. You are absolutely right. I could stick in an instantiation at the top, or in the other statement for that matter. I can leave the other statement blank if I really want to. Yeah. It's just stylistic. Somebody just asked that actually. It was down here. I could have said X or A, but I don't like to do that. I like to just use an intermediate variable instead. Just stylistic. I'm sorry? XA. Yep. Yes.
So does it matter which one numbers this as long as they're both less than your
It doesn't matter what. Well, it does matter what this is. I mean, another way that we could have gone about this is to, in this case, others. The only thing that it could be is 001. That's the only possible thing it could be. Oftentimes, what we'll do instead is just not write out the last case specifically and use others to accommodate that last final case. So omit this case that says when 111 and do others instead. Since 001 is not hooked up to anything in this case, that's a little bit dangerous. I don't necessarily want to do that. I could have a case for that, actually. I could say when 001, right? And then just leave it blank. I could do that. It's okay. It's not invalid syntax to do that. Not particularly unusual either. But this is required. I need this statement. It's absolutely required. Even if there are, well, yeah, even if there are no others. It's syntax. If you don't include a when other statement, it won't even compile. Yep. It won't even compile. It's required. I mean, what is it really doing there? It wants to make sure that no matter what, it's going to do something. It's going to take a particular path. Now, we're saying, well, I can force it to do nothing by just leaving it blank, but at least then it's chosen a path, right? At least then it's chosen a path to go down, and it doesn't have to choose ambiguously or not do anything at all, right? Any other questions about this example? Yes. Yep. This is an arrow. I would not pronounce that as less than or equal to. That's not what it is. It's an assignment. It's meant to be an arrow. I mean, I understand what you're saying. I just want to make clear this is an assignment statement, not a less than or equal to statement. So, I mean, yeah, you need to define. I've left some gaps, right? This is not complete. There are gaps here. That wasn't me. That was me being lazy, not me being, not me forgetting to do something. Yes. Yeah. Y is set to YA or C or D. right? Because we have the output of the decoder stuff here. We have C or D being fed into this circuit. Yes, that's what I just said. Yes. Absolutely correct. Yes.
Or could it be and could you do XA or A? Could it be wrong just in X or just do like XA equals A?
XA equals A?
Because wouldn't that basically be like the others case?
XA equals, well, I see what you're saying here because in this case it would be equivalent to whatever A is since it's ORed together. Sure. Sure, it's just more typing that you have to do though. It's not necessary, so that's just more time that your fingers have to spend moving. If you need the exercise, go for it. Any other questions? Okay, let's try another one. So in this particular circuit, we've got flip-flops this time. Right? I want you to write a process. It's going to be quite a bit different from this process. I see I've got some multiplexers here, right? So everything, let me make sure that what I'm saying is correct. Almost everything should be in a process in this particular example. See if you can fit as much of this circuit into a process as possible. You might not be able to get all of it in there, but try to put as much of this circuit into a process as you possibly can. Take a few minutes. I'll finish passing back the homework, and then we'll talk about this in a little bit. Guys, what are your names? Carter.
So essentially, as long as you're just looking at the clock,
There was actually a rising edge.
Yeah, S is 0 and C is 0.
I was doing my
Yeah, it's just,
I would
I think it has where to assign because like when you but I'm like it's probably so you have to do Y first. Yeah. And it's and it is one.
Okay.
We need
All right, let's see if we can piece this together. So what's gonna go in my sensitivity list this time? Yeah.
A, B, C, D, F, and then also Y.
All right. You said A, B, C, D. Say that one more time.
S, R, and Y.
Y and Z. Okay. Y is an output. So I'm not sure that y needs to be included for that purpose. Y is an output. Y is an input to that OR gate, right? But what's going to make y change? Y is going to change based on, it's like either B or C or D or, is that it? C is also an output. So I think those are actually covered, right? A, B, C, and D, I think you can make an argument for. Including Y and Z, I do not actually think should be included. S, I do like being included as it goes towards the multiplexers. Right, so that I agree with. The rest of the stuff, I think Y and Z should not be necessarily.
Do you need anything that isn't your talk and
Yeah,
those
so
are the only two things that actually cause the output.
and so I was gonna wait and ask this question again later, but since we asked now, let's talk about it. Do I need anything that's not the clock or A? So we consider B is only ever going to feed into a flip-flop. The flip-flop's only ever going to change based on the rising edge of the clock. So do I need B? Not really. Is it hurting anything? Not really. Right? It's extra. I don't need it. Is it hurting anything? No, not necessarily. Same thing for C and D. They're only ever going to feed into a flip-flop. That's the only place they can go. So the clock's got that covered. The clock's already got that covered. Same thing for S. S is only ever going to affect stuff that goes into a flip-flop. So the clock's got that covered. Right? A does touch an output directly. It's fed into this OR gate. So I do potentially need A, although I'm not even sure if A is 100% required. So, I think your best choices, while what we have there is not necessarily wrong, it's just extra. I think this is a good choice. I think taking A off could also potentially work. We'll maybe talk about that one at the end. But let's start with this A and clock. Okay. So far, so good. Let's see. So I've got my process. What do I need next? What's going to go inside of this process? What do we want to do? Yeah.
Well, I think one person is going to use check the rise.
Perfect. Yes. I want to check to see if it's the rising edge of the clock. So that's here's the syntax for that. If rising edge clock, then. So what do I do on the rising edge? What do I need to check for on the rising edge of my clock? What do I need to look for? I'm going to be reading stuff in, right, to these flip-flops on the rising edge. So I need to determine what the values are for each of these flip-flops, which in this case dictates Z and Y, right? So I need to have statements that are going to set Z and Y inside of this if statement. What does Z and Y depend on? What are the values for each of this flip-flop depend on? What's the first value that maybe we should take a look at? It's going to dictate. We start from the flip-flops and work our way backwards. Right? What's the first thing that I run into? A multiplexer. So what should we try to do to take care of that? Yeah, figure out when S is 1, or if you want to figure out when S is 0, that could work too, right? So what do I write down? What do I type in? Do that? Yeah.
One of the first things that you're going to take into account is that since Z and Y, like Z depends on Y and Y depends on Z and Y depends on itself, is you need to take into account the fact that processes happen in order. So you need to store what your old Y and Z are.
Good. Good. I'm glad you actually pointed that out. That would have come back to hurt us later for sure if we didn't think of that now. I need to store what the values of Z and Y are right now, right? Because they are being fed back into the remaining to the beginning of the circuit. So I need to grab that information right now. So I need to create some additional variables perhaps. Call them, well, X is bad because we have an X already. No, we don't actually. We don't. Oh, we do have an X. V, I guess, maybe. So I can say W set to Z and V is set to Y. Right? And then we of course would need to create these signals W, V, standard logic, right before our process, so that we have them available, right? Okay, so we've got our old values of z and y. And now, let's go back to what we were talking about before for the multiplexer. How am I going to implement these multiplexers? How have we done it in the past? How have we implemented multiplexers in the past? When statements. Is that going to work here? We're in a process now. So actually, I'm not sure a when statement is the best choice. Would it still work? I kind of think that it wouldn't. I kind of think that you aren't allowed to use when statements inside the context of a process. We've only ever seen them outside of a process, right? We've only ever seen them outside of a process. Inside of a process, we can use case statements. We can also use if statements. I think an if statement is the more appropriate choice here since we are inside of a process. So I would say, if s equals 1, then, okay, then we need to figure out what the values are going to be if s is equal to 1, right? So if s is equal to 1 for z, for example, then I want to read in, not z and a. But I don't want to use z here, right? What do I want to use instead? I want to use w, so not w and a. Okay, just double check. You can put this in if you want. That's fine. Right? Does that make sense? So far, so good. Then what do I need to do for the other value, y here? What's that going to look like? I've got b for not y, but the value that we stored for y, which is b. B for b. Everybody with me so far? So that's the case where s is 1. We took the top half for each multiplexer. Now we have to do the other case for when s is 0. Right? Where s is 0. Oh, well, actually, we have this other multiplexer down here, which kind of throws a wrench into things a little bit. If that multiplexer weren't there, we could just stick in an else statement and do this part. But we have to be a little bit careful. We need to code up this multiplexer first, I think. I think we should drop an else if in here to cover the case when, to cover one of these cases. I'm not even sure it matters which one in particular. When C and D, right? We can do it that way. When C and D. Else if C equals 1 and D equals 1. So what do I want to be the case then? When C equals 1 and D equals 1, I want C equals 1 and D equals 1. I want it to be Z, which is actually W. Right? So Z set to W. Which really just means it's maintaining its old value. It's just maintaining what it was before. You might be able to rewrite this in such a way that it's omitted. This step was omitted. Potentially. I mean, we need to have some way of covering this multiplexer, right? So, and then the last case, we could say else. Last case, that means s is 0, and this is also 0 here, right? So in that particular case, y is going to be set to c. C is going to make its way through to y, and z is going to be what? It's going to also be y, or in this case, we've been using v, right? So y would be set to c, and z would be set to b. I'm kind of running out of space here, but so we're getting pretty close to finish. What do I need to do next? What have I not covered yet? What's the missing piece here? Anybody know? Or anybody have a question with what we've done so far? We're not quite done. Yeah.
How do we just get the
My first else if.
like it's your else if?
My only else if. All right. So I need to have some way of distinguishing this multiplexer, right? You have some way of, looking at S will take care of these two for me. We'll take care of both. The first condition I wrote says if S is true, so that's going to take this path and this path. This multiplexer only feeds into the lower path. So if that statement fails, then I actually have two more paths. I have the path where this multiplexer is true and the path where this multiplexer is false. I could have written the else if the other way around. I could have written the else if as, when C and D is not true, and coded it up the opposite way. That also would have worked, right? But I had to do something there to choose between these two paths. I have a path for, the top branch of this mux and a path to the bottom branch. So there's three paths total, right? They both take the top, or this one takes the bottom, and this one takes this branch. This one takes the bottom, and this one takes this branch.
Why is it
Oh, okay. Well, let's take a look at that. So if C and D are both true, that's going to be this branch here, right? So where does this branch come from? It comes from Z. But remember, the old value of Z is what we set as W. One of the very first things that we did was we grabbed the old value of Z and set it to be W. So it looks circular here. I understand. So now I understand your question, right? It looks like we're going in circles. Z is set to W, and then W is set back to Z.
That multiplexer has nothing to do with C.
Yeah.
It should be Y set to W.
Yeah, that was my
Oh, I set the, thank you. Well, cool.
Okay, that is
Yeah, thank you. All right. Any other questions that I can make more complicated than they actually are? No? Okay. What are we missing? We're not quite done yet. We're almost done, though. We're not quite done. What are we missing? What's the part of the circuit that we haven't accounted for yet? Oh, have I been using the wrong values for things? Oh, I haven't said anything for X. Thank you. No, I haven't. That's it. That's the piece. Yeah.
There's also one more thing.
What's
With that else if statement, when else if C was on an equal sign, you also need to put in Z, set Z to B.
set Z to V?
Yeah. Because like Z is set to B when S is not 1, and that could either be, you know what I'm saying, one way when you have that logic in the final.
Set Z to V. Yes. Well, I think I see what you're saying. I only set Y here. I don't set Z in this case. So what happens then if we actually don't set Z and it passes through the process? I guess is the question, right? I think you're actually correct here. I think I do need to set a value for Z in this particular case. So what would that be? It would be just W, right? Yes, Z is set to W. Is that what you were saying?
I was
Oh, V. Z goes to old Y? Is that what happens? Oh yeah, that's what happens down here. Duh. Thank you.
yeah.
Thank you. I believe you're correct. Okay, so then the other piece that was just brought up that we need to tackle as well is X. We haven't done anything with X yet, so how do I do that? What do I say? Where do I say it? So let's think about what we've got here. I currently have two if statements open. I haven't ended either one yet. Right? So do I set X in this if statement? No, I'm going to close that one out. I think that one's good. I think I'm done with it. Do I set X in this if statement? I don't think so. I don't think that, so what would that imply? Setting it inside of that if statement means that X would only change on the rising edge of the clock, which means I would expect what? Rising edge of the clock implies flip-flop. There's no flip-flop for X. X is just there, right? So no, I don't think it's going to go on that one either. I think I'm going to close that out. So then where do I put the logic for X? I'm sorry? In a different process. Okay, that's an interesting suggestion. Let's talk about that. So what would that different process look like? Why would I need a different process?
Because whenever A changes with X
It is not dependent on the, well, is it not dependent on the clock?
changes,
So,
so Z is dependent on the clock. So you're going to always have Z dependent on the clock. But then you have a process that is based on A.
yep.
A changes, will change X.
So I agree with you. I actually like the idea of perhaps not doing it in this process at all. I actually like that idea.
Then you have to change the process.
I would have to take A off the sensitivity list. Yeah. So here's a question: Could I do it right here if I wanted to? Could I do it right there? I see at least a couple people nodding. The answer is yes. If I wanted to say X is set to what is it, Z or A? Is that right? If I wanted to do that, I think yeah, I could do that. I think I could do that. I don't see a problem with that, right? However, what Elizabeth brought up is this principle of separation, where I want to keep my asynchronous stuff separate from my synchronous stuff as much as possible. X is an asynchronous output. X is asynchronous. It's not based on a flip-flop. Y and Z are synchronous because they are coming directly out of flip-flops, right? So I could create a separate process for that if I wanted to. And if I had a lot of logic going on, I probably would. I could also say this and process, and then just do it here. X is equal to Z or A. I could just do it outside of a process entirely. Is that okay? Does that sit well with you? Does that seem all right? I don't necessarily need a process for this. How does a process work again? When does all this stuff actually happen? When do all those values actually change? So when the clock changes, I run the process, but I don't actually change the values as I go through, right? I queue everything up, and then at the very end of the process, I change everything all at once. Because it's a circuit, right? We're doing things in a circuit, which means it's going to happen not instantaneously, but near instantaneously. Right? So this would all happen at once, and it would actually happen at the exact same time that this happened as well. It would operate in parallel. Oh, shoot. I really want to do this next question. So we're going to do this, not this one. That question's good. But I really want to do this question. So we're going to do this on Tuesday for sure. But we're out of time. So have a great weekend. I'll see you guys next week.
Professor Shook?
Yeah.
I looked over the rest of the test. This is the only thing.
The only problem?
Yeah.
Okay, let me hang on to that for you, and I will regrade that as soon as I can and get it updated.
All right. Thank you very much.
Yep.
Very
expensive.
Yeah. Well, they don't bring it out in this class, but I'm looking for it. Thank you. I wouldn't know how to do anything. No worries, man.
You would no longer be
Yeah. Like, well,
Yeah, I do.
I'm not gonna call it.
One question I had, I noticed